In this video, we shall look at a couple of review problems associated with EMF and power in circuits. First, a brief introduction. Let's assume you have a battery, like that, and it's connected to a resistor whose resistance is R. The EMF of the battery is E. You have current inside the circuit going through the resistor, and if we ask what is the potential difference across this resistor V is quite simply IR, and in this case V is the same as the EMF of the battery. The voltage across this resistor is sometimes known as the terminal voltage, and in this particular case the terminal voltage equals the EMF of the battery. Now let's assume you have a battery, but this battery has an internal resistance to it. An internal resistance of a battery is labeled in a box together with a battery like that. And you have the same external resistor, capital R. Of course, you have current coming out like that in this direction. This is a positive terminal of the battery, this is a negative terminal of the battery. So the current through the main resistor is I as well. Now let's determine the terminal voltage here, the voltage across the resistor capital R. We know that the EMF E minus the potential drop across the internal resistor, let's call that resistance of that internal resistor, little r, and that is the voltage drop across the capital R. So this or that, namely V, is the terminal voltage in this case. And you can immediately see that the terminal voltage is less than the EMF of the battery. So we clearly see the appearance of internal resistance within a battery tend to lower the terminal voltage to be less than the EMF of the battery itself. Next, let's look at power. If you have a battery with EMF E and it creates a current I, provides the current I to the rest of the circuit, we say the rate of production of electrical energy of this battery, P, is I times the EMF, and the unit is of course watts or joules per second. So if we assume that this battery is connected to a resistor with a resistance R, the I, or the current that's passing through this resistor, is I, then we say as the current passes through the resistor, energy will be dissipated per unit time, and the rate of energy dissipation there is given by I squared R. And according to principle of conservation of energy, these two expressions must be the same. Let's look at the problems. Problem 1. In the circuit below, when that switch S, so this is the switch S, is open, the voltmeter V connected across the terminals of the battery reads 1.5 volts. When S is closed, the voltmeter reading drops to 1.38 volts. The ammeter then reads 1.35 ampere. Find the EMF, the internal resistance of the battery, and the resistance capital R. The voltmeter and ammeter can be assumed to be ideal. Let's deal with the first piece of information. Voltmeter measures voltage. It has very high resistance, and if it's an ideal voltmeter, you can assume there is no current passing through it. So when the switch S is open, this lower part of the circuit doesn't contribute. There is no current within the upper branch of the circuit, so the expression E minus IR equals to V will simply become E equals to V because there is no current. So we see, since the voltmeter reads 1.5 volts, we can immediately see that the EMF has got to be 1.5 volts. And that solves the EMF of the battery. Now we are told that when the switch S is closed, the voltmeter reading drops to 1.38 volts. And the current in the circuit as measured by the ammeter is 1.35 ampere. What that means is the current is going like that out of the positive terminal of the battery through the internal resistor and coming out and going through the main resistor, capital R, and again back to the negative terminal of the battery. So we can write E minus IR is I capital R, or E is I times little r plus capital R. EMF is 1.5 volts. The current is 1.35 ampere times R plus capital R. And we can work out the sum of the resistance as 1.111 ohm. In addition to that, we are also told that the voltmeter reading drops to 1.38 volts. Now what that means is the terminal voltage, namely V, the voltage drop across the capital R, is 1.38 volts. So using that information, 1.38 equals the current times capital R, from which you can solve capital R. It's 1.38 divided by the electric current, which is 1.35. And that's going to give you 1.022 ohms. Having found capital R, we can determine the little r, or the internal resistance of the battery, from this equation. It's 1.111 minus 1.022, and that's going to be 0.089 ohm. And this and that and that solves the problem. Problem 2. In the circuit below, find the current through 8 ohm resistor. 8 ohm resistor is that one. Find the total rate of energy dissipation in that 8 ohm resistor, and also the energy dissipation in the internal resistance of the batteries. Find the overall rate of production of electrical energy in the batteries. Comment on your results. Step number 1 is to determine the total resistance in that circuit. So you have 1 ohm internal resistor, 1 ohm internal resistor, and 8 ohm resistor on the outside circuit. They are all connected in series or side by side, so the total resistance of the circuit is 8 plus 1 ohms, which is 10 ohms. Now we determine the so-called net EMF in that circuit. Note that the 12-volt battery has a positive terminal connected to the positive terminal of the 8-volt battery. So that means the net of the resultant EMF in that circuit is 12 plus minus 8, which is 4 volts. And the current will go that way within that circuit. What that means is that current is the resultant EMF over the total resistance of that circuit. So the EMF is 4 volts, the total resistance is 10 ohms, and you're going to get 0.4 ampere for the current. So that's the answer for part A. Now part B. The total rate of energy dissipation in the 8 ohm resistor and the internal resistance of the batteries. So let's start with the 8 ohm resistor. The current through it is I, and we know I is 0.4 ohms. So the power dissipated, or rate of energy dissipated within that 8 ohm resistor is I squared times 8 ohms, which is 0.4 squared times 8 in the unit of watts, and that's going to be 1.28 watts. Now what about the internal resistance of the batteries? Similar calculation. The power dissipated in the top 1 ohm resistor is I squared times 1, which is 0.4 squared times 1, and that's going to be 0.16 watts. And the same goes for the power dissipated in the internal resistor of the bottom battery. It's I squared times 1. I is 0.4 squared times 1, and that is 0.16 watts. So the total power dissipated is therefore 1.28 plus 0.16 plus 0.16, which gives you 1.6 watts of power. And that is the answer to part B. Part C, find the overall rate of production of electrical energy in the batteries. So for part C, there are two batteries. In one battery, namely the 12-volt battery, chemical energy is converted into electrical energy. And we can calculate that. That is just I times the EMF. I is 0.4 ampere, EMF is 12 volts, and that's going to be 4.8 watts. In the second battery, namely the 8-volt battery, electrical energy is being converted into chemical energy. So the reverse is happening. And that conversion is at a rate of I times the EMF of the battery, which is 8 volt. So 0.4 times 8, which is 3.2 watts. This number refers to rate of energy production, namely the electrical energy production, and this plus this is the rate of electrical energy dissipation into some other forms of energy. And you see they should match. 4.8 watts equals 1.6 plus 3.2 watts, in accordance with principle of conservation of energy. And that solves the problem. As always, thank you for watching.